Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at National College of Ireland. And this video, another video in our series of videos on set theory, I suppose more importantly, I suppose we could really classify this video as following into our series on countability, is dealing with countable and uncountable infinite sets. And in this particular example here, we're going to try to show that z, the set of integers, is countable. Okay, and we're going to try to keep it as simple as possible. Yeah. Okay. So if z is countable, okay, if it's countable, well then we can list them. Okay, that's important. We can list them. Okay. We can list them. Okay, as an association. Okay, or as a bijection. Okay. Okay. With the natural numbers, with the natural numbers, and the naturals are defined by n. Okay, so let's just consider first of all what the naturals are. The natural numbers are the set of numbers 1, 2, 3, 4, 5, 6, and so on and so forth. And what are the integers? Well, the integers, okay, are the set of numbers minus 3, minus 2, minus 1, 0, 1, 2, 3, and so on and so forth. Okay, and what we'd like to show is that the set of integers are countable, or actually really what we're really going to try to show is that the cardinality of the naturals. Okay, we like to show that the cardinality of the natural numbers is the same as the cardinality of the integers. In other words, there's the same number of natural numbers as there is integers. Okay? Now, when we just look at this from a naive perspective, we can sort of see that the integers contain the natural numbers. So from here onwards is the set of natural numbers. Okay? And just at face value, when we look at it, the set of integers, okay, contain the natural numbers, also contains the number 0, and contain the negative counterpart for each natural number. So on face value and from a naive perspective, there seems to be more integers in the set of integers compared to the number of values or the number of numbers, okay, that are in the set of natural numbers. Because what we can clearly see here is that the set of natural numbers is contained within the set of integers. Okay? And what we're going to show is that the integers are actually countable. Okay? And once we show that they're countable, really what we're saying is that the cardinality of the integers is the same as the cardinality of the naturals. In other words, there's the same, these sets are the same size of infinity. Okay? And the way we're going to do this is we're going to list the integers. Okay? So what we're going to try to do is we're going to list the integers. Okay? Integers, okay, relative to the naturals, okay. Actually, I probably should have said we're going to list the naturals relative to the integers, okay. So what we'll do is we list the integers, or we'll list the naturals first, okay. So what we'll do is we list the naturals, okay. Here's the natural numbers, okay, and we're going to list them out: 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. And what we're going to try to do here is we're going to try to list the integers, okay, alongside each one of these particular natural numbers. Okay. Now, what's important is this: is that when we start counting the integers, okay, because that's what it really means to be able to list them. Okay, when we start counting the integers, we need to start somewhere. Okay, and we need to make sure that we count all possible integers. So I could say that 0 is the first integer, that 1 is the second integer, that 2 is the third integer, and that 3 is the fourth integer, and 4 is the fifth, and so on and so forth. But with this particular way of counting, what we'll end up doing is we'll end up counting from 0 all the way out to the right hand side through all the natural numbers, okay, from 0 then to 1, 2, 3, 4, 5, 6, 7, and we'll never ever get around to start counting the negative counterparts. Okay, So what we do is this, is we count like this. So we start at 0. Okay, we'll say 0 is the first integer. Okay, sorry, 0 is the first integer. Okay, we'll say 1 is the second integer. Okay, then we'll jump back across and say that minus 1 is the third integer. Okay, then we'll say that 2 is the fourth integer. Okay, then we'll say that minus 2 is the fifth integer. Okay, then we'll say that 3 is the sixth integer, and that minus 3 is the seventh, that 4 is the eighth, that minus 4 is the ninth, that 5 is the 10th, that minus 5 is the 11th, and so on and so forth in this particular fashion. Okay? And what we've actually constructed is we've constructed an association, okay, between each natural number, okay, and each integer value. Okay? So as you can actually see is that each integer value, okay, is associated with a natural number. Okay? And what we're guaranteed to happen is this, is we're guaranteed on this, through this particular column here, when we continue counting or listing the natural numbers, okay, we're guaranteed with this particular process, okay, to continually define the successor of each particular value in this list. So the successor to 8 is 9, the successor to 9 is 10. So what we're going to be able to do is we're going to be able to list all the natural numbers down here. Okay? And then what we're going to be able to do on this side is we're going to be able to list all of the integers, starting with 0, 1, minus 1, 2, minus 2, 3, minus 3. And what we can actually see that's happening is that we're starting here, we're counting here. Then we're moving out 1 and we're counting here. Then we count here, we count here, we count here, we count here, and we count here. So, but the important thing here is this, is that our process, okay, the process of counting, okay, or the process of listing, okay, is going to continually move out to the right hand side and also continually move out to the left hand side. In other words, it's going to cover the positive integers. Okay, let's exclude 0 for a moment. Going to the right, it's going to cover the positive integers, and going to the left, it's going to cover the negative integers. So this particular process that we've defined here, okay, associates each integer value, okay, the positive ones, the negative ones, and also 0, okay, it associates it with a unique natural number, okay. And the important thing here is that what we have here is we have the set of natural numbers here, okay, and we have the set of integers here, okay, and you can actually see with this particular construction, okay, that every natural is associated with an integer. Okay, so what we have here is that by definition, okay, once we can create a bijection between the naturals and the integers, now we haven't defined a function for this particular bijection, okay, I suppose we could define the function, okay, where f of 1 is equal to 0, okay, where f of n is equal to n minus 1, okay, and so on and so forth. We could actually define the actual function that represents the particular mapping, but we're not actually going to define it in this particular case. All we're interested in is showing that the integers are countable. By countability, by countable we mean that we can associate each integer. We can actually count each integer. Okay, but more importantly, what we've actually shown is that the cardinality of the naturals, okay, is the same as the cardinality of the integers. Okay guys, once again, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope that this video was somewhat helpful. Okay.